All right. Welcome back, everyone. So, sorry for the short break. So, we'll continue with Gordon Wichern, who is a senior principal research scientist at Mitsubishi Electric Research Labs, MERL, in Cambridge, Massachusetts. He holds a PhD from Arizona State University. And prior to joining MERL, he was a member of the research team at Isotope, where he focused on applying novel signal processing and machine learning techniques to music and post-production software. Before that, he was a member of technical staff at MIT Lincoln Laboratory. He is the chair of the AES Technical Committee on Machine Learning and Artificial Intelligence and member of the IEEE ASP Technical Committee. And today he will talk about XAI techniques that can be helpful in measuring the ability of large generative audio models. So with that, without further ado, I leave the stage to Gordon.
All right. Yeah, thank you, Chem, for the introduction. And yeah, thanks everybody for making it back in time. I know it was was not easy, and I appreciate seeing so many friendly faces in the crowd. So I'm Gordon, and today I'm gonna talk about some of the recent work that our group has done on audio generative models. And so as I'm sure everyone in this room knows, we've really been hearing a lot about generative AI, and this happens to me too. You know, MERL is kind of a small semi-autonomous research lab, but when people with like C's in their title start asking, you know, what are you doing about generative AI? And you have to answer, that something's going on. And many people smarter than me have started mentioning this thing called the Gartner hype cycle to me. And so we had this technology trigger of ChatGPT coming out in November 2022, and now everybody's crazy for generative models. And so since, people are asking me, what are we doing with generative models? I figure I better have something to answer with. So we started looking into these generative AI models for audio. And I think they can broadly be broken down into these two categories. So we have kind of the autoregressive transformer models, which are really kind of LLMs for audio. And the way these work is you first have, I have a picture here of AudioGen from Meta, but what you have is you have this convolutional neural network that generates a discrete latent variable, and then you can train autoregressively to predict these latents given a text conditioning. And so operating very much like a language model. And then the other kind of class of audio generative models, which is more inspired by these text to image models like Stable Diffusion and DALL-E, is latent diffusion models. And what these do is really treat like the spectrogram as an image. And so we saw, I think from Gail's talk earlier, that, the one unique audio thing here is the hi-fi GAN that kind of converts the MEL spectrogram back into audio space. But otherwise, we really have kind of just an image diffusion model that starts with noise and then iteratively denoises the spectrogram to generate the audio. And so I should say these aren't exhaustive too, right? There's other things that are in between here, such as like non-autoregressive transformers, and people are getting into flow matching is the next greatest thing after diffusion. But things that I think are interesting, and I'm happy that I'm able to work at a place where we can kind of study them, are these two questions. So one is, I'm curious how often these audio generative models are actually just spitting back out training data as opposed to generating actually unique sound. And I think that's a really interesting question to study. And the other thing is, Chem mentioned before I was at MERL, I was working on tools for like audio professionals, people who work in recording studios and stuff. And these text to audio models are really cool for like sharing, your HR policy turned into a song on Twitter or something. But I don't really see, they're not something that's really usable for like audio professionals yet. And I think it's interesting to think about how we can get along that path. So what I'm gonna really talk about today then is two works from our group. The first is going to be about the data memorization that I mentioned, and this was work mainly done by Demetrius Bralios from UIUC when he was interning with us last summer. And he's also going to be talking about this again at a lecture session on Wednesday. So if you want to hear about this work without all of my like silly context or whatever, I encourage you to go there and check it out. But so kind of why this idea of training data memorization is interesting is, you know, there's all these, we see these news stories all the time, especially in the US, about like lawsuits filed against these companies, right? And I'm not going to talk about these too much because this isn't the explainable law workshop or anything, but I do really like Sarah Silverman's quote that she calls OpenAI and Meta industrial strength plagiarists, which you know, may or may not be true. But I think there's really actually a technical question here that we don't really, at least I don't really know the answer to yet. And I think it's interesting to look into. And for the LLM and the image space, which has much more mature kind of generative models than audio, I think a lot of interesting like research is starting to emerge. And there's some pretty amazing stuff, you know, in the bottom left corner here. I show this work where these researchers figured out that if you prompt ChatGPT to repeat the word poem forever, it actually just starts spitting out the internet, the training data. And the amount of training data it spits out was purely limited by how much the researchers wanted to spend on API calls. I think that's since been closed, or the model's been better aligned. But you know, I think that just kind of shows the problem which is going on. And then there's this top paper from researchers at Maryland and New York University where they found a whole bunch of examples of the stable diffusion model where it was kind of obviously just, you know, doing essentially re-outputting the training data with maybe very slight differences. There's some other neat stuff. I like this idea where people to try to figure out what books ChatGPT was trained on, they'll like do a completion thing where they only will leave out like really obscure character names. And they assume that if it can complete these really obscure character names, then it would actually use these books to train on the model. But so we wanted to try to look into this in the audio case. And kind of the first thing that we had to do is come up with a definition of audio memorization. And so the definition we came up with, which I'll just read, it's on the top of the screen, is we define a generated sound file as a replicated training data when it contains nearly identical complex spectral temporal patterns. And so that's kind of a mouthful, but I want to decode it a little bit on kind of what we mean. And so the first is the patterns should be something interesting, right? So I said what we don't mean is things like white noise or constant tones. If a model is copying training data that's those, it's not really interesting, right? Because it's trivial to do. So it really should be copying something with more interesting audio characteristics going on. And then nearly identical is kind of a tough thing to define. But what we tried to do is to define it in terms of feature similarity. And we actually look at two kinds of features. So the first is this kind of contrastive language audio pre-training feature, which, you know, tries to put audio samples and their associated text in an aligned embedding space. And people use this all the time. And it's sometimes works good, but when it works bad, it's not really explainable and you don't know what it does. And I think what Demetrius really figured out is a nice way to actually find these generations that works quite well is to use like a really coarse Mel spectrogram and just turn that into a vector. And this is something that's very easy to explain. And the reason you want something coarse is, right, because you have these generative models and they're going through convnets, and these convolutional layers could have something like aliasing going on. You don't know what kind of artifacts are there. And so you don't want to like have the model key in on those. But if you make things coarse enough, then hopefully you just get kind of, you know, really broad spectral patterns and the onsets and offsets of the different sound events. And that can actually be really useful for finding matches. But I think it's also should be immediately clear that the kind of matches this thing is going to find are going to be things that are aligned in time and frequency to a decent extent, because otherwise the Mel spectrogram isn't going to match. So kind of the experiments we ran using this idea to find out how much these models memorize is we used kind of at the time of last summer, the best open source audio diffusion models. And I think I'll mention too, the first one is Audio LDM, which was kind of the original stable diffusion for audio model. And this model, as I mentioned before, it really works as an text to image model, but and then it has the hi-fi GAN that turns a MEL spectrogram into audio. One interesting thing that they had in audio LDM is they used the clap to train the model not only on audio where you had associated text, but you could also have just audio without text. And since the clap audio and text embeddings are supposed to be aligned, you could ideally use extra audio data to train the model. Then Tango was something that came out a little bit later, and it actually got rid of the clap, used a much more kind of streamlined and clear training process, and they just used an LLM to do the text conditioning, specifically FLAN T5. And at the time we started this project, Tango was the only model that had like the training code available. So that was kind of why we chose it and picked that to use in our memorization analysis. And so how do we find training data replication? So what we did is, we start with the generative text to audio model. We get a piece of audio and then we extract the features, right? And as I mentioned before, these features could either be the coarse MEL spectrogram or they could be the clap embeddings. And then we'd have kind of all of the training set, which we can also convert into vectors, and we can take the cosine similarity between these vectors. But the problem here is when you want to search a whole bunch of audio files, you need the comparison between all the files to be equal. But that's not really the case because there are some sounds that match with a whole lot of things. I mean, maybe we can think of white noise because it has all the times and frequencies there, but that's going to match with everything in the training set very easily. And so we want to kind of penalize that. And the way that we do that is this trick that's called similarity normalization. And what that does is we basically add a bias to the cosine distance score. And what this bias is it has some background data set of sounds. And if it's something that's close to everything in the background data set, it's going to have high similarities with its k nearest neighbors, hence a big bias, and you're going to downweight it. And if it's something that is far away from all the stuff in the background data set, it will have this low bias term and you won't downweight it. And so what this does is it allows you to kind of fairly and accurately kind of search for matches given the variety of audio that's used in the training process. And the other thing we wanted to do to kind of start this to make sure that we were kind of on the right track is to train models with smaller training sets to begin instead of on the whole full audio caps. And this is interesting. I think, we know a model is going to overfit. We can see it here on the standard training and validation set when we train with a small amount of data. But what happens here is now we know the model should be memorizing a lot of data if it only has 1,000 training samples. And this allows us to kind of get a good understanding of how this matching process that I explained on the previous slide is going to work. And here just kind of shows a visual analysis of what we found. And so the orange histogram, this is kind of the background similarity between all audio and audio caps. And so what this is you just take any two training samples, compute their similarity score, and you get sort of a background distribution of what you'd expect if there wasn't any training data replication happening. And what we can see is if we train the model on a very small data set, we have much higher scores for the generated audio. It's clearly kind of copying the data. But as we increase the size of the training set, the distributions start to overlap a lot more. And we also noticed that there's a lot of similarity in the training set, which I'll get back to in a second. And the other thing that I just want to mention quickly is now we can look at kind of copied examples from the 1,000 training samples, 5,000, and the full model. And I think what you can see is what's interesting here, especially in the 5,000 cases, kind of the failure cases of the two feature representations. So in the second row here, we see the MEL is failing to find like a pretty obvious training data replication. And then in this third row here, it's actually the clap that fails. And so I think a lot of previous studies have just looked at like clap similarity as a way to find matches. And what we found when we tried to do this controlled experiment is without similarity normalization. And even for a lot of these cases, we needed to do the MEL spectrogram to actually find them. And so these now are some examples from the full model that we found that are seem to be pretty decent candidates, sorry, for replication. And all right, so this is the prompt. A power tool is in use. And what you can see, there was a training data that was called a high-pitched drilling, which I'll play. I think the interesting thing here is, right, the person who was operating this generated drill happened to push the buttons at the exact same time, but the frequency characteristics are a little bit different. And I think what you can see here is the MEL sort of matched these onsets and offsets very well. The clap returned something that I would say is not an accurate replication. And then here's another example of somebody snoring. I mean, it's interesting that, we have a sample of the training set of a person snoring where they snored 3 times, at a certain frequency distribution, and that's what gets generated when you ask the model for a person snoring. Here's kind of, just some more examples that show sort of the difference in the different techniques for kind of finding these. The top is an explosion twice, and again, the MEL kind of finds these very similar onset characteristics where the clap totally misses those, just really focusing on kind of the semantic language in the text. But then here's kind of a funny case of where the MEL totally fails. Because the MEL spectrogram kind of has energy in similar patches, and it actually confuses a winged insect with a man speaking and a toilet flushing, just because the distribution and energy is the same. Oops. So the last thing I wanted to talk about here is what we did find also when doing this is, audio caps, which is a subset of audio set, is just audio scraped from YouTube, right? And when we started looking for what the generative model was memorizing, it became quickly apparent that audio caps had a whole bunch of copies in the data. And we were a bit surprised because audio caps we thought was like a well-curated part of audio set where people tried to write text captions for it. But what it turned out is there were 257 kind of really obvious duplicates. And I think a lot of them were taken from YouTube videos that all came from like the same YouTube channel, and the person put the same like little intro jingle in the front. And there was also a whole bunch of like videos of, Obama like throwing the podium down, uploaded by like a lot of different people. And so I don't know, that's just something that's interesting. And I think people in like the text and image modeling community have started thinking that what the model memorizes, if these samples are kind of overrepresented in the training set. We actually didn't find that in this case, but I think that question still probably requires further investigation. And so just kind of wrapping up, manually verifying and listening to a lot of these examples that we found for these audio caps type things, we saw approximately 5 to 10 per 10,000 training samples were pretty, like, even in the full model, pretty high confidence matches. We also seem to notice that audio features such as like event onsets, offsets, kind of durations of events seem to be more replicated than the exact like acoustic timbre. And I think really if we want to accurately like search for memorization in generative models, it's important to probably use a basket of representations as opposed to just something like clap, which is really a black box and does weird things sometimes. And I think though there's still, many questions left to answer, like kind of how do the text prompts actually influence what the audio is memorizing? As I mentioned a little bit, data set duplication. And there's also a whole bunch of tricks in training these diffusion models, which I think is interesting to think about what they're memorizing, things like classifier-free guidance and other types of data augmentation. So with that, I want to switch to the other thing in my talk, and this is work with our intern Tony Koo from here in Seoul. And it's a paper we just put on archive. And this is about probing generative music transformers. So let me talk about what I mean. I think I mentioned this a little bit at the beginning, but before I came to Merle, I used to work for this company where I built tools, that were really, we tried to sell to audio professionals or people who at least wanted to be audio professionals. And this was when like deep learning was kind of exploding on the scene. And I was like, wow, look at all these cool things that they would do. And then you would put it in front of customers and they'd be like, yeah, but there's nothing to do with it. It just outputs an enhanced speech. I want to control it. And it quickly became inherent. We had to use algorithms that people could control either before or after the deep learning processing. So for the speech enhancement and source separation, we really focused a lot on like time frequency masks because there were a whole lot of biases you could build in there that people could control that you can't do if it's something that's just generating the signal. And I mean, similarly too, when we used like classifiers and stuff to make decisions on how we would suggest processing audio, we made sure that we output those decisions in the form of a preset that people could still kind of like tweak and mess with. And so now in this slide, for anybody that was here in the morning, I'd like to like close your eyes and imagine you're looking at Ethan's slide from the morning, because his was actually a much cooler illustration of this, in terms of wanting to control these like text to music generative models. And so, right, if we want these to be something that, audio professionals really want to mess around with, it's one thing that I like about these transformer models that operate on like a frame by frame autoregressive basis is that kind of is more how we work with audio as opposed to something like diffusion, which just outputs like a full spectrogram at once. And so I think if these models ever were to become real time, that would be pretty neat to be able to tweak this autoregressive thing while it's generating. But right now, the way you condition these models is pretty global, right? With text or sometimes things like melody. And so what we want to do is try to figure out how we can build knobs that people can use to kind of like tweak the guts of this audio transformer. And we don't even want to define the knobs. We want to like get even more ambitious and actually let people build the knobs themselves from a few examples. And so how we're going to do that is we, this whole text to audio transformer thing is inspired by LLMs. So LLMs have, since they're such a, hot area right now, everybody's working on them. There's a lot of kind of neat tools that have come up for how to sort of tweak them at inference time without training. And so one thing we liked, which came from down the street at Merle at Harvard, is this technique called inference time intervention. And this was something that came up with to make LLMs more truthful. And the way that it does that is it has a data set of correct answers and wrong answers for different prompts. And then it runs all those through the LLM, and it looks for the activation of each attention head in the model, not just the layers, because it finds that actually if you try to kind of steer entire layers, things get a little bit too wacky. But if you do just individual attention heads and try to steer those to be more truthful, you can actually surgically kind of steer this LLM at inference time to make it more truthful. And so we're like, oh, that would be cool. Wouldn't it be cool if we could take, Music Gen, the big audio generative model that from Meta, and could we use a similar technique to try to figure out how to sort of build your own knob for Music Gen for whatever you want? And so the way that this works is we use these probing techniques, and this is kind of, I think, a very classical, explainable technique, which is basically you take some intermediate output from a network and you make a simple classifier on that. And then you say, if that simple classifier is good, then the network has some understanding of that concept, right? And this really doesn't require a huge data set, right? Because we're just talking about really basic logistic regression models. And so we tried to do some simple experiments where we would just add instruments to the the Music Gen thing. We could just build a knob to like turn up the amount of drums or the amount of guitar in an instrument. We also tried something where could we use these knobs to make Music Gen sort of more realistic, and by training the model on outputs from music gen, but then also real music and having it distinguish that, and then could we steer that? And there's also more probing tasks we looked into. Actually, Tony has a poster back there if you want to learn about this in more detail. But kind of in the experiments, we tried two things to do this. So obviously, the text to music is the use case we're mostly using, but to kind of understand this in a bit more controlled thing, especially when we're adding instruments, is we did this audio continuation. So we'd give the model a few seconds of audio that didn't have the instrument we wanted to add with the intervention, and then use that to fill up the attention buffer, and then use this inference time intervention to see if it could actually add the instrument. And so kind of the way this intervention process works is, here I just sort of wrote one of the ways you can write down the multi-head attention process. And really what we're doing is we're just adding a bias to the output. And this bias, though, is kind of a few different factors. One is kind of the overall intervention strength. I just realized I spelled it wrong. But so this is the thing that the knob would allow you to tweak, right? How much bias is there? And then there's the intervention direction. And what this is so we have these examples that are both have this audio characteristic and do not have this audio characteristic. We have our simple classifier. And so really what we want to do is we want to move this the output of the model in the direction towards the characteristic that we're trying to steer the model to have. And so the intervention direction is just that direction we're trying to steer the model. And different heads have different amounts of spread in the data along this intervention dimension. So it's important to normalize them by that spread. And then the last thing, one thing we found that was really important to make this thing work for music that they didn't have to do in the LLM case was to have something where if we just tried to do the steering every time, the attention buffer quickly got filled up with all these steered modified audio samples and the model just diverged into chaos very quickly. So we came up with this self-monitoring idea, and that was kind of our model. We called it Smitten. And as I mentioned, this was because the direct application of ITI quickly made music gen kind of incoherent. And so what we found is that if we do this self-monitoring process and we add this into the intervention operation, it actually makes things sound a lot better. And really what this is quite easy. So we're just adding ITI to the music transformer. So we have these probes and we're trying to surgically steer only those probes that have this musical characteristic. But then what we're doing is we're also actually monitoring the outputs of these probes to make sure that if they already actually have that characteristic, then don't keep steering the model and potentially make it go crazy. And so here's kind of just a quick illustration of how that works, right? So we have the audio, we have these probes, and this is a music sample where we know when there's actually drums. And what we do is we can compute the kind of the top K attention heads that actually were sensitive to drums, and we could compute statistics over those attention heads, things like median, mean, standard deviation. And then we can use those to come up with sort of a heuristic threshold, which we can use as kind of the threshold for that monitoring weight, which decides whether or not we should add the intervention. And so here's just an example of what I mentioned when we just tried to directly apply the LLM intervention technique to this case of adding drums. And as I said, we have a quick snippet at the beginning of the clip, which is the audio that doesn't have drums, and then we're going to steer it to add the drums. All right. So it went kind of crazy. And here's the thing with the self-monitoring. You can see now it's adding the intervention a bit more intermittently, only when it needs it to get the desired result. I mean, it goes on for a while, but I'm going to ask you to take my word for it that it never goes crazy, at least in the full 30 seconds that I had in the clip. So some other interesting things we found about kind of how this works is really the quality of the probes that we learned. Like, so if music gen was really good at detecting the presence of a certain instrument, for example, you can see it drums and bass, it has attention heads with very high accuracy of detecting these instruments. And actually the model turned out to be quite successful in having the intervention, but for other types of instruments like piano, it was less good at, we were less good at finding probes that were sensitive to that, and the success of the intervention was lower. And I think I mentioned this at the beginning. One neat thing we found that you could do with this is you could actually train the model to maybe generate coherent music longer by making these probes where we first took output generated by music gen, and then we took, real music, and we used that to train the probes. And then we tried to steer it in a more realistic direction. And so let me play the sample. Well, maybe you can kind of see it in the spectrogram, right? It's like what we listened to before. The audio plays and then the model kind of quickly becomes sort of incoherent after about 18 seconds. And then similarly, we could just add to the text prompt, make the music more realistic. That didn't seem to help. But then when we used the smitten, actually, it generates, a 30-second long sequence of more coherent music. And the last thing I want to talk about in this topic, which the credit for this idea goes to Jonathan LaRue. But I don't know, and I hadn't seen this video in many years, but I don't know if anyone has seen this Saturday Night Live skit where Christopher Walken is the audio engineer recording this band. Will Ferrell is the cowbell player. And Christopher Walken keeps saying, I want more cowbell. I want more cowbell. It's driving the rest of the band crazy, and it's really obnoxious. This guitar player here is actually Jimmy Fallon. And when you watch this, he can't keep a straight face. He's just cracking up the whole time because it's so silly. So we're like, all right, can we use Smitten to actually build the more cowbell knob? And what we did is we just downloaded some cowbell samples from Freesound. You use a beat tracker to, make them rhythmic cowbells. And then we train the probes with the music with and without the cowbell, and we apply Smitten. So here's what happens when we just prompt music gen to add more cowbell when it's completing a piece of music. All right, so it didn't really add cowbell. There was some weird rhythmic thing going on, but here's what happens when we use the Smitten with the more cowbell probes. So it doesn't really sound great, but I find it a reasonable facsimile of the Will Ferrell banging on the thing. And so wrapping up, then I just want to, say some final things about, what we did, what the limitations are, and what I think is interesting kind of in the future about, explaining audio generative models, since we're the explainable AI workshop. So the first is that these, I think Ethan mentioned this a lot in his talk this morning, but inserting like explainable inductive biases into these audio generative models is really essential, especially for audio professionals, to have something that they would actually want to use and maybe give them kind of the feedback that they crave. And I also think things like this are fun because they allow you to break these things in really kind of creative ways. And the other thing, the first part of the talk, I talked about memorizing training data, which I think is incredibly fascinating, but there's still really a lot to learn. And I think one thing that I'm really excited about, and I think is how can we actually harness this way that these models memorize their data. If we could really understand this better, maybe there's things that we could do to provide like fairness to training data people when their data is copied or how much it's used in these models. And so I think this is really an interesting area to study and something I'm very excited to see more work come out of the community about. So with that, I'm done. Thank you.
Thank you very much, Gordon. So Are there any questions? There's.
Okay, thank you. So maybe I have no question, just one comment, because I'm doing the NLP and the language model projects, not the audio and the speech project. So I think for your first presentation, you found some duplicated YouTube audio. But from my experience, I think you can use some deduplication algorithm from the NLP, because you can transfer the audio to the text and then process it. So I think maybe you can do it and improve your data quality.
Okay. Yeah. Yeah. That's an interesting idea. Use
Okay.
use like a captioning.
Yeah.
A
Okay. Thank
captioning
you.
model to deduping. Thanks.
We have time for a few questions actually. So, yep.
I want to make sure I'm understanding Smitten. So if I wanted to take music gen, and since I'm a clarinetist, I don't care about cowbell, and I want to make a new more clarinet.
Yeah.
Can you like maybe in an elevator pitch describe what I would need to do?
Yeah, absolutely. So you would need to get, let's say, a handful, maybe of, I would say 10 music samples without clarinet. And then you would, source separation style, mix in some clarinet. In the cowbell, we tried to do the beat aligning thing. I don't know if you necessarily have to do that. We didn't A/B whether it's necessary. But now you have this data set of clarinet, no clarinet. You train the logistic regression probes on the, so you run each of the samples with the clarinet and without the clarinet through the music gen. You get an activation. All the samples for each attention head, you get all the activations, you train this logistic regression, you find the K that are most sensitive to clarinet, and then those are the ones that the knob kind of moves towards clarinet as you're generating the music.
Okay, cool. Thank you. That was now one question on that then. When you say an attention head, you're talking, do I take the output after it goes through the normal sort of conventional fully connected layer and change that? Or am I changing where I multiply keys by values and that kind of thing?
You're doing it after that, but before the attention head. So I don't know if you can see the equation here. You know how when you do the multi-head attention, you kind of parallelize the heads and then you concatenate them back together before you do the MLP. So you add this thing before you concatenate the heads back together. So you do the attention, and then before you concatenate the heads back together, you add this bias, and then you concatenate them back together and go through the MLP.
Cool. And last question, then I swear I'll stop.
Okay.
So now you've got this approach, and the approach that I might take just with prompt engineering is add like double the clarinet, extra clarinet, more clarinet. Have you explored that to see just how much?
Absolutely. So that was, when we did this, that was kind of one of our main baselines, was like add the instrument. I think with the realistic music, we said like add more realistic. We tried adding, high quality realistic music, things like that. But I mean, we didn't try like hardcore prompt engineering, what was the best prompt to use for music gen, but we did try kind of the obvious one, and this worked a little bit better.
Okay, cool. Thank you.
You have time for one more question. Anyone? If not, oh.
Thanks, Brian.
All right. Yeah, I mean, yeah.
So can I ask something? It's actually related to what was just asked. Did you try to also probe the impact of the text conditioning to kind of see if there is some intervention that you can take also directly on the prompt, maybe in the latent space instead of in the text space?
Yeah, that we have not tried yet, but I think that's an interesting idea to look at in the future. Right now, we just left the prompt or whatever other conditioning, because you can also prompt music gen instead of with text with like a chromogram, for example. But yeah, we haven't looked into that yet, but I think that's interesting thing for the future.
Thanks.
All right, so let's thank Gordon once again. And we will move on with two talks from two contributing works. So